Hello everybody, it's Mrs. Pound and I'm back with another video from Chapter 2 about matter from BJU Chemistry 5th edition. Our topic today is from Section 2.2, Energy and Matter, and this is part 1 of 2 parts. So our objectives today will be to explain how the origin of energy fits in with the laws of thermodynamics, compare temperature, thermal energy, and heat, and explain exothermic and endothermic processes and give an example of each. So first of all, we need to know what energy is. And energy is the ability to do work. And we talked about in physics how energy and work have the same label because they are interchangeable, okay, basically in our equations. There are two states of energy, and they are kinetic energy, which is the energy due to an object's motion. So we see this owl in flight, it is moving. So if we see the energy causing an object to move, that is kinetic. But there can also be potential energy. This is energy of an object due to its position or condition. So in these batteries, there is stored chemical potential energy. Also, if we were to place an object up high on a shelf, it has potential energy if it is knocked off the shelf that can become kinetic energy. So there's also an interchange between kinetic and potential energy. When can be converted, they can be converted back and forth. There are 6 forms of energy that we talk about. The first is mechanical energy. This is things that move, like the clockworks in the background. When you're walking, when you're riding a bicycle, that's all mechanical energy. There's also thermal energy. This is the sum of the kinetic energy of the particles in an object. According to the kinetic molecular theory, all atoms and particles are moving, and molecules. Some are moving faster than others. Gases are moving very fast, zipping around. Liquids are sliding past one another, and solids are vibrating back and forth in place. And all of that is thermal energy because those particles are moving, and it's the sum total of that energy. Now, there's also acoustic energy, which is sound energy. So the person playing this guitar is producing acoustic energy. There's electrical energy due to the movement of particles, especially electrons. So we have electrical energy. And then there's electromagnetic energy, such as light, radio waves, X-rays, gamma rays, infrared. All of those are electromagnetic waves that travel at the speed of light. And there's nuclear energy. Here's a nuclear reactor, silos, the cooling towers in the background. So nuclear energy that comes from interactions in the nucleus of an atom. So what I want to talk about now is thermodynamics. This is the study of the movement and conversion of energy, especially thermal energy. Thermodynamics was basically born due to steam engines. As steam engines were created, they started studying them, and so thermodynamics comes from that study. And so in the background we have here a flame heating some water and some teapots, and so there would be movement and conversion of energy taking place there, especially thermal energy from being transferred from the flame and the natural gas to the water in the teapots. Now, the first principle I want to talk about is the law of conservation of mass energy. This states that matter and energy cannot be created or destroyed, but can be transformed or transferred between objects. And a lot of times we state these two laws separately. However, we can put them together because of Einstein's equation, E equals mc squared, and their mass and energy are also interchangeable due to Einstein's discoveries. Okay. This law is also known as the first law of thermodynamics. Now, the first law of thermodynamics is problematic for naturalists regarding the origins of the universe because a naturalist cannot explain the source of matter and energy from his perspective. Cannot explain where these things come from. Sometimes they say it's cyclic, but even if it's cyclic, where did it originally come from? This differs from a creationist perspective because both agree that energy is converted to different forms, but creationists believe that all of creation and scientific laws have their origin in God and that the total amount of mass and energy created from the beginning has remained constant, just as the law says. Now, the second law of thermodynamics states that all natural processes tend toward the highest entropy and minimum usable energy. Entropy can also be explained as disorder, and as we can see in the background, this looks like smoke in the background. And as smoke rises, it dissipates, it becomes more disordered. The energy from that smoke becomes more, is less useful perhaps, and it spreads out. So it's going to higher entropy. It's becoming more dispersed because entropy is the measure of dispersal of energy in a system. So the energy in that smoke, those smoke particles, is dispersing and spreading out. When we talk about things like entropy, we have to look at a system. And a system is everything within a set of boundaries defined by a scientist that is being studied. So you can have different systems depending on what you are talking about. But the reason we have to have the boundaries is because otherwise we have to include the whole universe, and that's just too big for us to look at completely. So here, our system might be a fishbowl. Okay, that's an example of a system. It could be something that is defined that we are studying. Or the system could be a mud puddle. It could be a pond. It could be an entire watershed. It could be the entire planet Earth, but we have to define the system that we are looking at, especially when we're talking about thermodynamics, because we just cannot look at the whole universe. And one important thing we need to understand too is that the energy in a system becomes less usable when energy increases. According to the second law of thermodynamics, this is why when we are converting energy, it's never 100% converted into the form that we want. For example, incandescent light bulbs take electrical energy and convert them to light or electromagnetic energy, but it's not completely efficient because they also give off a lot of heat. And the more energy that we put into that, really the less usable it ends up becoming. There will always be this dissipation. Now, heat is the movement or flow of thermal energy between regions having different temperatures. It always flows from regions of higher temperature to those of lower temperature. So that is always the way heat flows. So heat and thermal energy are not the same thing, okay? Heat is the flow of the energy. And then there is temperature. This measures the average kinetic energy of all the particles in a sample. Now, the focus here is average. Okay, the average, because thermal energy and temperature are different. Thermal energy affects the temperature, and temperature gives us an idea of the thermal energy, but let's say you have boiling water, and you have a liter of boiling water, and you have a drop of boiling water. Now, both of them have the same temperature. Both have the same temperature. But if you were to spill them on you or get them on you, which one would cause the most damage? The 1 liter would cause more damage because it has more overall thermal energy because there are more particles there, even though it's the same temperature. 1 drop is probably not really going to burn you, but a liter of boiling water will burn you. So they can have the same temperature, the same average kinetic energy of the particles, but have very different total amounts of thermal energy in them. There are also what we call exothermic processes. These are chemical or physical processes that release thermal energy. These are things that when we touch them, they feel warm because the heat flow is from the object to our hand. So we feel that it is warm because the heat is flowing to us. Some examples are burning natural gas, explosion of a firecracker, dissolving certain substances like calcium chloride will produce heat, okay, that will be transferred to us and it will feel warm or hot. The opposite of this are endothermic processes. These are chemical or physical processes that absorb thermal energy. So something like ice melting. Ice melting feels cold. So these are processes where it feels cold. So put in parentheses after this, feels cold. Okay? Because what is happening is the thermal energy, the heat flow is from our hand to the ice cube. Because it's taking energy from us, it feels cold. Okay? So that's why ice feels cold, because it's taking energy from us to melt the ice. An example are the chemical cold packs. You know, the cold packs where you gotta hit them or crush them or whatever. There are chemicals in there that when they mix, they produce what we call an endothermic reaction, and it feels cold. Also, baking soda and vinegar, when you mix those two chemicals, they will feel cold. So our objectives for today's video were to explain how the origin of energy fits in with the law of thermodynamics, compare temperature, thermal energy, and heat, and explain exothermic and endothermic processes and give an example of each. So don't forget your 5 questions, and I'll be back with another video.